Hi everyone, I am Dr. Surjit Singh. In this video on Python via examples, we shall talk about the use of random numbers in Python. Let us begin. In this session, we will explore the Monty problem and delve into its statistical analysis. We'll examine the use of random numbers in Python and apply the statistical methods to solve the Monty problem, after which we'll discuss how to interpret the results obtained from statistical methods. Finally, we'll summarize the conclusions. Monty problem is well known in the field of probability. It became famous because there has been a long debate before its solution was finally accepted. It is based on a game in which there are three doors. One of them has a car behind it, while the other two doors hide goats. To win, we must correctly choose the door hiding the car. After we make a choice, the host opens one of the two remaining doors that he knows has the goat. He then asks us if we would like to change our mind. Most experts initially assumed that switching the selection would not matter, believing the odds were evenly split at 50-50 between the two remaining doors. However, Monty Hall, the host of the game, played the scenario with Marilyn Savant, a woman with an exceptionally high IQ. She took a different stance and, despite strong initial skepticism, ultimately proved the experts wrong. Let us now learn about the statistics of the game. At the start, we have no information about what is behind the doors, so the probability of finding the car behind every door is 33%. We write these probabilities of the car at the top of each door. Let us choose door 1 as our initial selection. According to the rules of the game, the host then opens one of the two remaining doors. Suppose he opens door 3. This must be a goat. He gives us the option to change our selection of the door before concluding the game. Now that the probability of the open door has reduced to 0, how will the probabilities of the remaining two doors change? Will the probabilities change to 50-50 amongst the two remaining doors, or will it be transferred only to the unselected door, which then becomes 67%? We will show here that this second distribution of probabilities is correct. The probability of the door that we had selected was 33%. This remains unchanged regardless of any subsequent actions, such as the host opening the remaining doors simultaneously or one by one. So, under the present set of choices, door 2 has higher probability than door 1, and it is to our advantage to change the selection to door 2. Let us discuss the two choices of the car door one by one. If door 1 indeed hides the car, both the other doors must have goats behind them, and switching of the selected door would result in a loss. Therefore, in these cases, sticking with our original choice is beneficial. However, the likelihood of this scenario occurring is only 33%. 67% chances are that door 1 does not hide the car behind it. For these 67% cases, car must be behind door 2, and shifting our selection to door 2 is to our advantage. In case the host opens door 2, it means that there is a goat behind it, the car must be behind door 3, and once again, shifting our choice is favorable to us. This means that shifting our selection increases the chances of our success from 33% to 67%. Practical way of finding solutions to such problems is to play the game a large number of times, in which the input positions of the car and the goats are selected randomly each time. At the end of all the trial games, we count the percentage of them in which the result is favorable to the hypothesis. This is where Python programming is helpful. Random numbers play an important role in probability experiments. Python has a module for this and we import it. We will simulate 1000 random trial games, though we will print the details for only first 30 of them. We start two counters with 0 as their initial values. First counter counts the number of trials in which success comes on staying with the original choice. The second counter counts the number of trials in which the success comes upon switching our choice of door. After printing headings, we start a for loop for 1000 trials. In each trial, we assign random numbers between 1 and 3 to the car door and the selected door. These trial values are purely random and are not in any way correlated to each other. It means that they are chosen independent of each other. Selected door may have the car or a goat. Sure goat doors is the list of doors that do not have the car and are not selected. The host won't open the selected door, so he opens one randomly from the sure goat doors list. Selected door and the open door are always different. We now find the position of the third door, that is neither the selected door nor the open door. If the selected door is the car door, our action is to stay at it, while if the third door is the car door, our action is to shift our choice to it. We now proceed to count the two actions separately. We remember that if the selected door is the car door, the favorable action is to stay at the selected door and we increase its counter by 1. While if the third door is the car door, switching is the favorable action and we increase its counter by 1. With this, the trial game is over. We repeat these trials 1000 times with different random positions of the car and the goats, though we print only the first 30 as the sample output. After all the trial games are over, we find the percentage of matching trials and the trials in which switching of the door is the favorable action. Finally, we print the results. Let us now have a look at the output after all the 1000 trial games are processed and analyzed. This is the output report of a typical run of our program. However, we may note that because of the use of random numbers, the output is never exactly same in different runs of the computer program, but they are close to each other. First 30 lines of the table are displayed in detail that are followed by the report of 1000 trial games. All these trial games are selected randomly that are independent of each other. Let us magnify a part of the output for better readability. In every trial game, Cardor takes the value 1, 2 or 3. Test conducted on these 1000 values of the car door shows that each of the three doors appear 33% times in the series of trials. Select door also takes a random value out of 1, 2 or 3 in these trial games. Their occurrence is also 33% each in the series. Further, we can verify that the choices of the values in the two series are independent of each other. This means that the correlation coefficient between the choices of car door and the selected door is 0. Such tests are important for probability experiments, otherwise the conclusions are erroneous. Random module of Python assures that it produces truly randomized lists. In the first set of trial values, the car door and selected door are both 3. So, in this game, the host can open either of the gates 1 or 2. Python randomly opens door 2 on behalf of the host. Under the same situation, in a later trial, it opens door 1. If car door and selected door are both 1, Python on behalf of the host randomly opens either door 2 or door 3, while if car door and selected door are both 2, it may open either door 1 or door 3. In all these cases, the selected door is same as the car door, for which we must stay at the original selection of the door. We count the number of all such trials in which stay is the favorable action. This count turns out to be nearly 33% of the total cases. In the remaining 67% trials, switching is the favorable action. In these trial games, the door selected by us is not the car door. Host won't ever open the selected door or the car door. It means that the open door is different from both of them, which is the third door that is neither the selected door nor the open door. Therefore, this must be the car door. Summary of the 1000 trial games is shown at the end of the output. The results are in line with our arguments. If this Python program is repeatedly executed, in each run of the program, wins on switching are found to vary between 64% and 70%. As we increase the number of trial games to 10,000, this success rate converges to a narrower range that is between 66% and 67%. Results of the program conclusively establish that switching the choice is favorable to us. All the experts who believed that opening one of the three doors gives 50% chances of winning to both the remaining doors have been proved wrong. The 33% probability of the originally selected door does not change if we open the doors one by one or all of them together. Actually, the three doors divide themselves into two groups, the door selected by us and the remaining two doors. Only 33% chances are that the selected door is the car door, while 67% chances are that the car door is present behind one of the two doors of the other group, which must become a revised selection. Opening the door with the goat helps us in precisely deciding the position of the car. If he opens door 3, car is at door 2, while if he opens door 2, car is behind door 3. Doors 2 and 3 have 33% chances each of having a goat. On opening one of them, their chances get transferred to the other door in the group. This explains that probabilities of the group of these unselected doors redistribute amongst themselves from 33% each to 0 and 67% upon opening one of the two doors of the group. Even if the number of doors is more than 3, when the status of some of the doors of unselected group of the doors become known, their probabilities redistribute amongst the remaining doors of the group and no portion of their probability is transferred to the originally selected door. In this session, we discussed the Monty problem and probability of finding the car in the three doors. We then used Python to generate random numbers in different ways and used them to simulate the Monty game. We then performed the statistical analysis of the results of large number of games. Finally, we concluded that the probability redistribution takes place only amongst the unselected doors. Hope you enjoyed the video. Please feel free to ask for further clarifications on my email address given below. I'm looking forward to your comments. Please stay tuned for more such videos.